Professor John A. Rogers.
Thank you very much. All right. Well, thank you so much for that kind introduction. It's a real honor and pleasure to be here and to share with you some of our research in this area of personalized health. Is sort of a combination of material science and electrical engineering, very interdisciplinary in a sense. And so it's been a great visit so far. Really enjoyed the interactions that I had with faculty and students yesterday. Got a tour of this incredibly beautiful campus, and that was a real treat and a real delight. And I'll have a chance to tour Monticello later this afternoon. And so really looking forward to that. And so I want to thank the foundation, the Jefferson Foundation. See, my slides are kind of locked up here. Let me see if I can get them going again. There we go. And so you guys know more about the history of this campus, obviously, than I do, but I did a little bit of background reading and study a little bit. And, you know, it's just incredible, you know, these giants that you know, exist in our past, these incredible geniuses. And I think Thomas Jefferson fits into that category, an incredible polymath with, you know, incredible insights into politics and architecture and higher education and so on. And so, of course, author of the Declaration of Independence when I think he was 33 years old or something. And I went back and read some of the prose that was involved in that document. And it's just breathtaking, you know, the kind of elegance in the writing, you know, the crispness in the conveyance of these powerful ideas, and just the bravery, I think, that was embodied in that document is really you know, astounding in many ways. And so, you know, just pulled one of the quotes here. I won't read it, but it's really remarkable just in terms of the English literature and the command of the language and the vocabulary. And I thought this is really amazing. And it's like a skill set that is really rare even today. But then I thought, well, now we have ChatGPT, so it doesn't really matter what I can do. So anyway, just wanted to say that and kind of acknowledge the foundation for their generosity in making this lectureship possible, and also to my former postdoc, Bao Xing, who's a very accomplished independent faculty member here, for sort of putting this together and thinking of me kind of in this context. And so over the next 45, 50 minutes, I'll kind of go through a whirlwind of technologies and materials and different things that we've been doing in the area of engineering science, specifically the intersection between engineering and medicine. And so it's all about kind of skin interface wireless bioelectronic systems, and I'll describe what we mean by that in the context of health monitoring, sports medicine and clinical medicine as well. And then toward the end of the talk, a little bit more kind of exploratory efforts that we have in integrating haptic capabilities into those same engineering platforms. And I know there's a lot of really outstanding work in this kind of broader area here, University of Virginia, to sort of acknowledge the contributions that this community has made to this broader space. But I kind of just focus on work out of my own group in this particular presentation. So I apologize, there might be a little bit too much content here. I'll go pretty quickly. But if you have any questions, I'll be around and more than happy to kind of discuss some of the details if you have more granular questions or uncertainty about what I'll be presenting. So what is bioelectronics? It's really the idea of electronics built for biology. So you think about consumer electronics gadgetry, it's really built around sophisticated classes of man-made microsystems, but they're built out of materials and geometries and with mechanical characteristics that are really incompatible with long-term intimate integration with soft living tissues. And so that creates kind of an opportunity for research, is how do you reformulate those classes of technology to be biocompatible in that sense. And integrating electronics with the brain would be a great example of that. It's a hot area these days, neurotechnology in particular, and using that kind of capability to sort of tease out the fundamental operating principles of the brain, but also control brain behavior and establish new classes of human-machine interfaces. And so I think probably most people are familiar with that. But if you can accomplish that brain-compatible electronics, you wouldn't want to stop there. You think about taking that same kind of technology and integrating it with other sort of vital organs internal to the body, or the skin, which is the body's largest organ, and a position for relatively non-invasive integration of electronics. But thinking not only electronics, but also microelectromechanical systems, microfluidic lab-on-a-chip technologies, optoelectronics, all sorts of things that are currently built on rigid planar platforms. How do you begin to sort of recast those into forms that look more like skin or more like the brain or the heart. And so this is a broader area that's very active for research, and it's one where we've been we've been pursuing different ideas over the last 20 years or so. At Northwestern, we have an institute dedicated specifically to this area. And again, it's really a construct that helps us bring together experts in various areas of engineering science with medical practice and medical science ultimately as well. So it's an endowment associated with that and allows us to really build things at a pretty high technology readiness level, founded on basic scientific research supported by the usual federal agencies, or at least in the past that's been the case. We'll see what happens in the future, but allows us to kind of extend things out to a level, in many cases, allows to do pilot scale studies on human subjects, as I'll describe as I move through the presentation. But just to restate the goal, what we're trying to do is create electronics for biology, and that's what bioelectronics is all about. And so thinking about the sophistication and function that's provided by state-of-the-art silicon CMOS integrated circuit technology, but not on a rigid silicon wafer platform configured to be compatible with soft time dynamic living tissues. So thinking about integrating integrated circuit technologies on, around, or throughout soft living tissues in a chronically stable manner that will allow for two-way communication, monitoring, and also control of biological processes. And I think that's a overarching vision that has a lot of relevance for what we believe will be the future of healthcare. So within that space, we have kind of three buckets of activities as a way to maybe kind of organize things. One, starting on the left, is the idea of skin-like electronics, so very thin membranes that could interface on the surface of the body, the surface of the skin, the epidermis in particular, but the same kind of technology could wrap the heart or the brain, the spinal cord, peripheral nerves, so very thin skin-like membranes with sophisticated capabilities in electronic function, wireless data communication, power supply, wireless power transfer, that kind of thing, either in the form of sheets or filamentary probes, so hair-like probes that can support functionality of that sort as well for point contact location into interfaces into the depths of tissues. The other sort of illustrated in the middle of this slide is this notion of bioresorbable electronics, very interesting area for us as well. And you can kind of think of it by analogy to a resorbable suture, but instead of just providing kind of a relatively dumb mechanical function in the context of a suture, hold a wound closed, now we're talking about advanced digital electronic functionality, wireless communication, and so on, and building up classes of electronic materials that can support that function, but also have this unique defining characteristic that they can dissolve in biofluids to biocompatible end products. So temporary implants is what we're thinking about there. We have a number of activities in that space. Kind of know pretty much what we're trying to do in terms of medicine and biological research in those first two areas. The third one, a little bit more exploratory, really thinking about how we can create classes of microsystems technologies that don't exist in dense 2D multi-layer stacks as sheets or filamentary probes, but actually span volumetric spaces in open sort of mesoscale network type geometries, at least conceptually analogous to what you would see in a neural network or a vascular structure in the body. So you could interact throughout volumes with living tissues, kind of blurring the distinction between technology and biology and kind of putting it all together. And I think that for us is an interesting direction. I won't say anything about that middle direction or the one on the right. We just focus on the one on the left here. And in the spirit of, I think, our founding fathers and so on, who were for the most part practical men, thinking about practical technologies and engineering and innovation and invention and that kind of thing. I'll also include not just the underlying material science, mechanics, a lot of the engineering science associated with these devices, but really try to touch upon our efforts to do translation, to get things out of the academic lab into scaled deployments where they can be more useful to society. And so I'll include in my presentation a bit around our activities in that direction, but really focus on this technology here on the left. And so you can think about a skin-like device as a kind of wearable, but radically different in form factor, mechanical properties, and ultimately capabilities in monitoring underlying physiological processes related to health status. So many different types of wearables, but if you take a look at what's commercially out there, they're all basically small, rigid pucks that loosely couple to the body at the wrist, sometimes the finger, And that can provide a lot of interesting levels of functionality, but not that relevant from the standpoint of clinical grade monitoring of parameters that physicians know how to interpret and are currently collected in a hospital setting, like in an intensive care unit, for example. And the reason why they don't support those kinds of measurements is they don't really afford an ability for a persistent, imperceptible, sort of comfortable, intimate physical interface to the skin, which is really needed for a lot of measurements that are done in an ICU context. So we started thinking about this actually before that category of devices even existed, wearables, that is. This was probably a 2008, 2009 timeframe when I was on the DSRC study group, as sort of a advisory group to DARPA. We thinking about, what would be the ultimate sort of in body integrated electronic technology? What would the form factor look like? And we decided the ultimate would be something that offers the kind of functionality you can achieve in a rigid, planar, conventional form of electronics, but embodied in something that would look more like a kid's temporary tattoo. So you could put it on the surface of the skin. You would forget that it's even there, totally imperceptible, able to accommodate natural motions of the skin with that kind of persistent, intimate skin interface. So these are some of the kinds of physical parameters that we were thinking about in that context. So, ultra thin in geometry, very light in terms of aerial mass level, and very low in modulus, as low as you could go, I guess, to minimize any kind of mechanical constraint on motions of the skin. Not only flexible, but stretchable. Your skin stretches. It doesn't just flex. So we're thinking about beyond flexible electronics to something that can accommodate large strain deformations. So those are sort of physical parameters, but also something that would be air and water permeable to avoid accumulation of moisture at the interface between the devices and the skin, which can lead to irritation. So it need to be air and water permeable, but at the same time, the active electronic materials would have to be waterproof to avoid degradation that would otherwise follow from exposure to sweat or transepidermal water loss, for example. And then the question is, how do you do that? How do you begin to put together a material science set of capabilities, manufacturing, and so on to realize technology of that sort? You can think about maybe 2D materials or carbon nanotubes or polymer-based semiconductors, small molecule semiconductors, and sort of build up a whole new class of electronic materials to kind of do this with sort of the naive, kind of straightforward notion that you want a flexible or stretchable device, you probably have to use flexible, stretchable electronic materials. And we spent a lot of time going in that direction. I think it's still really interesting from the standpoint of academic research. But what turned out to work better for us from a practical standpoint, and really thinking about translation, is to blend hard, conventional electronic materials with soft, polymeric materials in strategic layouts that give you effective mechanical properties comparable to those of the skin, but with materials that can support high performance capabilities and sort of leverage all of the scientific and practical engineering know-how that exists around conventional wafer-based electronics. And so the ideas there are pretty simple. Instead of a silicon wafer, we use silicon nanomaterials, ribbons, membranes, wires, that kind of thing, thick enough to support the electronic functionality that we want to achieve, but very thin, and as a consequence, mechanically flexible due to the cubic scaling of the rigidity with thickness. So that provides sort of a building block material you can put on a sheet of plastic. You can begin to build very high performance monocrystalline silicon-based flexible electronics. But like I said, the skin not only flexes, it stretches about 20, 30%. So you have to think about something that could not only bend, but stretch more like a rubber band. That's a different type of mechanics that you can achieve just by making materials thin. But if you take the thin material and you put it on a soft elastomer, not in a flat geometry, this kind of wavy shape, you end up effectively with something that resembles an accordion bellows. So you can stretch it, you can compress it, the wavelengths, the amplitudes of these nanostructures of silicon can change to accommodate those end-to-end deformations without imposing strains that could lead to fracture in the silicon material itself. So this is kind of ancient history, and I don't want to spend too much time. I would just kind of give you a sense of what's worked well for us. You can think about that as a base idea, and then you can add all sorts of engineering elaborations on top of those two really simple concepts. Here's an example of that. You don't have to think about just isolated straight ribbons. You can think about interconnected filamentary serpentine mesh structures. So you can exploit in-plane buckling, in-plane wavy shape, as well as out-of-plane. And if you do that with quantitative attention to the mechanics of how these hard mesh structures come together with soft elastomeric matrix materials, you can really dial in any kind of effective stress strain property that you want. and put all the hard materials on these filaments, and then the mechanics can be dominated by the surrounding elastomer. And so in this case, we've engineered this system, which includes silicon on those filaments and sort of semiconductor device components with stress-strain properties, effective elastic modulus that's comparable to the skin, maybe 150 kilopascals, in spite of the fact that this mesh includes silicon, which has 150 gigapascal modulus, so a million times stiffer. But you create this, there's kind of like a metamaterial, I guess, in modern vocabulary. That's kind of what it looks like. This very simple idea, but you can get a little bit more sophisticated. You think about the skin. It's not simply a linear elastic material, but actually the tangential modulus begins to increase at a strain level of about 20–30%. Ultimately, it's tears, but the stiffness will increase. And so you end up with this like J-shaped stress-strain behavior. And it turns out with this kind of construct, you can match not only the linear part of the stress-strain behavior of the skin, but also the full J-shape response, because as those filaments begin to straighten out, now you're pulling on the hard material itself. And so it very naturally becomes stiffer and stiffer as you begin to strain it to a larger and larger degree. So anyway, just from an engineering exercise standpoint, you can go off and you can do inverse modeling and inverse design. So the skin has different properties depending on where you are across the body. So the abdomen has slightly different, characteristics than skin on the back region of the back. This is real skin, so measured properties, the open symbols here. This is finite element modeling for optimized geometries of mesh structures, and then from the FEA and the inverse modeling, you go off and you build this experimentally, and you can really quantitatively match not only the linear response but also the J-shaped response of the skin. So you can do a lot with those simple ideas. Now, if you want to make a complete system, now you have to think about materials, mechanics, and circuit design all together at once. So you get the mechanics right, but you have to have the right materials, and it has to have the right topography, obviously, sort of interconnected to provide the system level functionality you ultimately want to achieve. So it's material science, mechanics, and also electrical engineering. Now, I'm a material scientist, so sort of my core expertise in electronic materials. So I like to think about these things as hard, soft, hybrid material systems, like deterministic composites in a sense. But an electrical engineer would take a look at this and look at it as a really strange layout for a circuit, because you have overlaid on top of the circuit level functionality, the requirements and mechanics. So anyway, that's kind of the overview, and you can begin to do that. So this is a first demonstration. This is not system level in terms of the functionality. It's just a platform of all the kind of building blocks you'd ultimately want to achieve in an integrated circuit, but with that full skin-like physical set of characteristics. So thickness, modulus, mass, water vapor transmission properties, and so on. That's what it looks like. It's almost like a second skin. So that temporary tattoo vision sort of realized in a platform like this, you peel it off, it looks kind of like skin. It's not even rigid enough to support its own weight. So that's what it looks like. So then again, a little bit of ancient history. I'll bring you up to speed here in a second, give you a sense of state of the art, but this is just historical. You might think about when that happened. So this was 2011. We got started, like I mentioned before, 2008, 2009, pushing in this direction. But the first wearable device wasn't launched commercially until 2013. So it really preceded that entire category of technology, but it is sort of a wearable device in that sense. Now, I mentioned that we're interested in translation, so we got started pretty quickly after that first paper, put together a company, raised money around that, built an engineering team, ultimately created a commercial version. We started around 2009, 2010, before that publication, so it's a little bit misleading here, but it was all 1 year after the publication. FDA approved for cardiopulmonary health monitoring in 2015. So I think this is the first stretchable electronics product. It's not the full skin-like embodiment that I just showed you, because I had to think about manufacturability and that kind of thing. But still, quite thin and stretchable, soft, that kind of thing, like a Band-Aid almost. I have a few in my bag if you're interested in taking a look. I can let you handle those. So this turned out to be sort of an engineering effort. It didn't incorporate the appropriate level of medical insight into how these devices could be inserted into a clinical workflow. That was one challenge with this particular company. The other is that the medical community just wasn't ready for this kind of technology. There was no, wearable technology. Fitbit is coming a little bit later. It's not medically relevant, and so people really didn't know what to do with this. But from a commercial standpoint, there was a lot of interest in the pharma industry for doing digital clinical trials, so monitoring quantitative endpoints associated with new drugs. And so there was some success there, a few $1 million of revenue per year, and then it was ultimately acquired by Metadata, which is a division of Dassault Systems in 2021 to add to their portfolio of digital tools for doing clinical trial support. So I'll come back to this in a second, but just a little backstory on our first pass at an attempt to commercialize this, which worked at some level, but it didn't really realize what I had as an ultimate sort of aspirational goal of sort of changing the way we do healthcare. And so I'll give you a sense of where we are on that second. So we and others have put together a broad portfolio of different kinds of wireless body interface devices focused on clinical grade measurements where there is a clinical predicate, but also thinking about de novo monitoring capabilities, many different types of sensors, many different types of form factors, but all with an eye toward continuous monitoring, clinical grade, not only in a hospital, but in a home is kind of the goal. And so, over time, there's quite a number of options here, many different types of sensors. And again, we're not the only people active in this area by now, many groups doing great creative work in this space. And this is kind of a list of the different types of sensor modalities that are now available, compatible with a kind of soft skin-like device platform. So precision thermal, you can measure thermal transport, hydration, thermography, electrical, come back to this, ECG, EEG, that kind of thing. Sweat, you can embed microfluidic channels into these platforms, give you a sense of what that's all about here in a second. Mechanical, you measure strain, motion, modulus pressure. You can include light sources, photodetectors into these platforms, so you can do oximetry, for example. You can also do very high precision measurements of body sounds at, again, anatomically relevant locations for those measurements, because the devices can be placed anywhere on the body because they're skin-like, and almost in any place on the body can represent a comfortable point of interface, selected based on the clinical need and the measurement goal. And then each one of these sensors can be embedded in a device, or you can take multiple collections of those sensors, make them multimodal, each one, and then you can have multiple sensors mounted at different locations across the body, wirelessly time synchronized, so you can get full body health parameters out in that way. Clinical quality, again, where there's a clinical predicate, but also think about de novo, not just in a hospital, episodically measured, but continuously, so big data. Come back to that in a second. And then it turned out to be a very interesting thing about cost as an engineering performance metric in a sense, because we wanted to develop technologies not so expensive that only wealthy people could use them, but actually with cost structures that would allow anybody around the globe to sort of access and benefit from this technology. And I'll give you a sense of what we're doing along those lines in a second. So I mentioned with MC10, that was back when I was at University of Illinois, did not have a medical school. So we were not like as intimately integrated into the medical community as I think in retrospect would have been of benefit to us. And so that was a main motivation in my move from University of Illinois to Northwestern. And we have this institute that allows us to really kind of mix it up with the clinical community. And we decided, maybe the most compelling opportunity in a clinical care context for these kinds of technologies would be in the context of premature babies, which are currently monitored 24/7. They're in a very fragile health status, but monitored with engineering systems that were originally developed for adults and just mapped onto these very tiny, fragile babies. And it just doesn't work well, as you can probably imagine. I won't step you through the disadvantages here. It's also expensive because you have a box of data acquisition electronics over here, so $20,000 for a GE Dash system, for example. And then from a cost standpoint, each one of those devices is just single use. And so they're thrown away after each cycle. So the vision, and this was 2016, 2017, was to get rid of all of that, replace it with a couple of these skin-like wireless devices, and improve the care of this very precious class of patient. So that's what we did. I'll just fast forward. It's a number of topics I want to get through here. All of that can work. So you can reproduce all of the vital signs monitoring that's done even in a level 4 NICU, like the one that we have at Lurie Children's Hospital downtown Chicago, with 2 devices with that full skin-like construction. So these are battery-free, so they're operating by wireless power transfer. They're also fully wireless data streaming. Device here goes on the chest, device here goes on a limb. So you measure cardiac and pulmonary function here. You do blood oxygenation with that device. So because of our relationships with the medical community in Chicago, specifically neonatologists at Lurie Children's Hospital, we were able to get IRB approval of those devices for use on actual premature babies coming through the NICU. So this hand here is Aaron Honvas. He's head of the Department of Neonatology For IRB studies, we can't eliminate the FDA-approved wired-based system, so we're just adding technology on top of the babies, but to validate it. And so then we have a quantitative comparison between data streams off of our device to the clinical standard for purposes of validation. So we did about 200 babies in that way, all the way down to 26-week delivery. In this particular case, 24 weeks is the edge of viability. So about half of the 24-week deliveries don't make it. So this is right as small as you would see, in a modern NICU, and we do graphical user interfaces so the nurses can interact with the devices in a simple way. So that turned out to work pretty well, and then we expanded out in the pediatric intensive care unit. This is at Prentice Women's Hospital, also in Chicago. Bigger babies, but still benefiting from a wireless skin-like alternative to the kind of wire-based systems that are used today. So you see the device on the chest, it's the epidermal device. There's a transmission antenna that sits in the base of the chair or the base of the isolate, in the case of babies back in the incubator, delivering wireless power to the device and also capturing data wirelessly. Streaming fashion. So this is doing ECG and surface temperature, which is pretty good approximate to core body temperature in this sort of hospital context. And then from the ECG, we get heart rate variability, respiration rate. And then the other device, you can see it down here. The receiver unit is on the base of the foot, and you can see the LEDs and the photodetectors. There's two color photoplasmography, so you get blood oxygenation from that device. And then these two devices are time synchronized. You actually get hemodynamic information, so you can measure how long it takes a pulse of blood initiated by a cardiac cycle here to reach that part of the body. And that kind of pulse arrival time measurement can be correlated in certain instances with a calibration factor to blood pressure. You can capture a lot of information. So that was spring of 2019. There's a lot of popular press interest in that work, as you might imagine. And so we were contacted by program managers at the Gates Foundation, Save the Children organization, asking whether we could recast that technology into a form that would allow economically viable deployment into lower and middle income countries where there's no monitoring technology at all, wired or otherwise. And so that's what got us interested in thinking about cost as like an engineering performance metric. How could we achieve the same kind of measurement capabilities, but in platforms that would allow for economic viability in various countries in Africa, for example, where you measure the economics in terms of the cost per patient monitoring day is the way you think about it. And you have to have a certain cost. It's 10 cents per patient monitoring day is the way you need to think about it. So we put together an approach and a budget and sort of scaled the economics and work with the Gates Foundation to do that. And then they provided large funding stream to allow us to go do the engineering. So we did that and then published the results 1 year later. A little bit different, more like that MC10 device ultimately, aligned with manufacturing practice and consumer electronics gadgetry, designed to be not single use, but multiple cycles of use, hundreds of cycles. This is the only way you can amortize out of the cost per patient monitoring day, the cost of the device itself. If you use it enough cycles, then the cost of the device doesn't really matter. So the overall architecture is very, very similar. It's binodal, multimodal sensor suite. And then that worked out well, and we validated the devices, the same kind of IRB studies that we did for the original epidermal devices, but these are more like a Band-Aid, I guess. That's a raw data, ECG, two-color PPG. And then we actually go beyond clinical standard because they have a high bandwidth accelerometer in the chest unit. So we get cardiac sounds out for free in a sense because it's very low cost additional component to add. And it provides information that's complementary, not just redundant with the ECG. You get valve openings and closings. You also capture respiratory cycles because you're monitoring motions of the chest wall. So that's a raw data. The physicians really only look at distilled parameters from that data, like heart rate, SpO2, respiration rate, temperature, that sort of thing. So anyway, that worked pretty well. This was the first deployment, again, using boots on the ground provided at the Gates Foundation. This is a couple of my students up in the front of the room in a hospital or health facility in Zambia. I was taking a picture here. This is the end of 2019. I think it's December 2019 before the pandemic and all that. But this was good. It was actually at this point that we realized we can't really continue to do things at this scale with an academic team. But we can do other kinds of technology development efforts, and Gates was interested in not just neonatal pediatric health, but upstream from that maternal fetal health. There's a lot of mortality happens during childbirth in Africa. And so could you monitor the health of the mother, health of the fetus during the intrapartum period, and then use that information to improve the way the patients are cared for? So the same devices that we developed for the neonates could be deployed on expecting mothers. And then we added a third wireless platform for measuring uterine contractions and fetal heart rate. And it's all sort of time synchronized together. So that was the second Gates program. And then the idea here is not to just use data to determine instantaneous health status of a given patient, but collect population scale data. So you could determine not only instantaneous health status, but maybe health trajectory. Where are things likely to go? Is there going to be a complication? When is the birth likely to happen? And so on. So that was the idea, a common data platform, all collected with similar data technology, or device technology. And then with clinical labels on outcomes, and then develop machine learning around that. So this is 487 pregnant women in Zambia, show up to health clinic, mounted with the devices, monitored through the intrapartum period up until the time of birth, and sort of track that. This is heart rate and respiratory rate and SpO2 and systolic blood pressure from that hemodynamic measurement. So this is where things were headed. Now, tragically, 3 of the women that were engaged in this study passed away, and this is a tragic thing, but it's not enough from a statistical standpoint to train a machine learning model. And so I think everybody was aware of this, and this is sort of a pilot scale attempt at doing that kind of thing. And so just last fall, Cybele Health, now this is the company, sort of the engineering-oriented company that's enabling a lot of these studies. So it's not like a California-style startup. There's no VCs involved. It's just like, focus on engineering and deployment, philanthropy, and LMIC is one focus. So it was a $20 million grant that was provided last year to really scale this up. So I'm not directly involved in Cybele's operations, just co-founder and board member, but I'm really interested in kind of what's going on. So I was in Africa end of 2019, and then went back again as part of the launch of this larger maternal fetal program in January. And so we were in Nairobi, Kigali, and Lagos, and that's meeting with various healthcare professionals and doing training and this kind of thing. So this is our attempts, not the end of the story by any means, but in order to build a sustainable business, you have to focus not on just on LMICs and philanthropy. There has to be some kind of commercial thrust as well. And so I think we put a lot of the pieces in place for that, with partnerships with companies that already have presence in medical device technology and hospital relationships and so on. And we did the first wireless NICU in North America in Children's Hospital in Montreal, just to give you a sense of that. And then kind of the latest, I would say, milestone achievement is we won the account for Denmark. So they're moving to a wireless patient monitoring strategy. It was an open, very competitive process for different companies coming in and bidding and talking about their technology. And so Cybele's partnered with Draeger, and they won the account. And that deployment is just starting now, and I'll be in Denmark next week to kick things off. And that was a program that was announced in the late fall. So that's what it is at this point. It's not just that chest unit and that limb unit, but really a broader portfolio of wireless monitoring technologies, all under a common data platform. So there's a real opportunity to feed AI in healthcare in this particular context. And these are some of the numbers of 20 countries at this point, not just Africa, obviously, India, Pakistan, various parts of South America. And these are the kinds of numbers that represent the current status. So ongoing, project, I think, headed in the right direction. We're hopeful that this will pan out. And that's the Cybele team at this point, about 100 people. Almost all engineers. The CEO is a medical doctor, which I think, given the MC10 experience, you really need that medical expertise embedded directly. It can't be just engineers building stuff. You really have to understand the clinical workflow, reimbursement, FDA approval, and all that kind of stuff. So I just want to mention that. So let me kind of shift gears now. And so most of the sensor modalities I've described up to this point rely on sort of biophysical measurements. You're measuring biopotential or temperature or flow or motion or body sounds, that kind of thing. But if you really want to get a deeper insight into health status, you'd like to get biochemical markers of health as well. And you typically do that with blood or interstitial fluid, both of which require penetration of the skin. So it becomes kind of an invasive device approach, and you have risk for pain and infection, all different things. And so Around 2015, 2014, we got interested in thinking about eccrine sweat as an interesting but relatively underexplored class of biofluids to be captured non-invasively. And we begin to think about whether we could go through the same process of reformulating silicon integrated circuit technologies to look like the skin. We do the same thing with microfluidic lab on a chip technologies, traditionally made out of glass materials on rigid substrates. Could we make those skin-like? And it turns out you can, pretty straightforward to do that. So you can build soft microfluidic devices, very thin, very low modulus materials, elastomers. You can mold channels and valves and reservoirs. You can adhere them to the surface of the skin. It's a closed microfluidic system, but with openings in the backside to find inlet ports. And those inlet ports can be aligned to holes cut into a bilayer biomedical adhesive that bonds the device to the skin. So as the eccrine sweat glands activate, they push sweat up through these openings into the inlets and then through this network of microchannels and reservoirs where we can capture and store the sweat for biochemical biomarker analysis. And one way to do that would be sort of combine stretchable electronics on top of this for electrochemical assessments, but then you have to worry about radio and battery, and we're always thinking about cost again as an engineering performance metric. And so instead of electrochemistry and electronics, we decided to focus on colorimetric chemical reagents for doing color-based analysis of things like lactate and glucose and creatinine and urea and other kinds of biomolecular species that are present in sweat due to diffusive equilibration between those species in interstitial fluid and blood and the sweat glands. So it's all kind of mixed up. There's all kinds of chemistries in sweat. So that's what it looks like. This is the first platform of that type that we published. So it has 5 inlets, one in the middle, filling up this serpentine channel. We have a color changing chemistry here that goes from purple to red when in contact with water. So you just identify the color change front to determine how much of that channel has been filled up. You can determine the local sweat rate and sweat loss from that. And then there are 4 other inlet ports that connect individually to these 4 circular reservoirs, each one of which contains a color-changing chemistry that's responsive to a biomarker of interest, in this case, lactate, chloride, glucose, and pH. So it's a very simple device, single-use, recyclable, also compostable if you choose the materials appropriately, but providing quite a bit of information around sweat and, by extension, biochemical health markers and status. So like with the electronics, really important to think about mechanics and adhesion and soft materials integrated with the skin. In this case, maybe even more challenging than the electronics and the applications I mentioned before, because now you're thinking about integration with the skin in the context of what could be vigorous rate of sweating and also pretty extreme mechanical motions of the skin. And one way to solve that is just use super glue. You really adhere it tightly to the skin, and that way removal becomes a problem. The other way to do it is to make the device as soft as possible and as thin as possible. And if you do that, you reduce the interface stresses that would otherwise tend to drive delamination, thereby making it much easier to establish a robust adhesive interface to the skin. So like before, you have to think about mechanics, materials, system design, adhesive interfaces, and so on. And so with our collaborator, Young-Gang Huang, we do a lot of FEA modeling and use that modeling as a guide for material selection and choice of overall geometry. But you can do that, and you can build systems that do sustain a waterproof interface to the skin, a watertight seal for precision measurements of sweat, sweat loss, sweat rate, and biochemistry of sweat. This is an example of one of the devices on the outer forearm, compatible even with a little bit of hair. Not a problem. It's a soft material, so it can kind of conform to the topography associated with the hair. And in this case, you can see the sweat is filled up to that 7 o'clock position, and then these reservoirs are filled up. And then what you do is you just take a digital image, and then you do image analysis, color extraction. You get quantitative information out of that. So here's a device on my inner forearm while I'm working out. And so in this case, it's a serpentine channel back and forth. There's some color food dye in the inlet port here. So I start at 5:52, I'm working out, begin to fill this thing up, filling it up. I'm taking pictures at different time points. At about this stage, I get really ambitious, see if I could fill it all the way up. Almost kill myself at this point trying to get it all the way, but able to do that. So it's like a time-dependent tattoo is almost the way you can think about it. One of the interesting things here is you look at the adjacent region of the skin. There's no accumulation of sweat there. Of course, that's because evaporation is occurring. That's the whole point of sweating, is you get evaporative cooling. But what that means is, especially if you're in an arid environment, you sort of lose track of how much water you've lost due to sweating because you don't really see any sweat accumulation. But in this particular case, you can realize, wow, you lost a lot of sweat, actually. They don't really see anything on the skin. So this is kind of an awareness thing. I'll come back to that in a second. But the other thing is super simple measurements that haven't been possible before. For example, you can measure cumulative sweat loss as a function of exercise time. In this case, I'm on an elliptical running at a pretty constant intensity. But the amazing thing is the extent to which the sweat glands are operating at a fixed rate to within uncertainty. It's like really amazing, you know, how precise the body is controlling sweat rate depending on physical load in that case. So sweat loss is one thing you worry about in sports and athletics and that thing. Electrolyte balance also, because your sweat has electrolytes in it. And you need to worry about that also. So we sort of focus on this colorimetric chemistry for measuring the concentration of chloride in sweat, which is more or less electrostatically balanced with sodium. There's a little bit of potassium. When you measure chloride, you get a pretty good estimate of electrolyte level in your sweat. Everybody's sweat has a different salinity. It depends on your genetics, depends on diet, it depends on exercise, depends on season, things like that. But this particular assay covers the entire physiologically relevant range from 10 millimolar to 125. And the color change is vibrant, even for channel depths that are only about 200 microns. So you just snap a picture, you pull the color out, and you can do almost as well as you know, analysis by HPLC. So about plus minus 2 to 5 millimolar, something like that. So you can do pretty well with that. So we published the first paper in 2016. I then got a call from the president of Gatorade, wanted to make a device out of it, wanted to provide it to their customer base so the customers know how much sweat they're losing, how much electrolyte they're losing, and then you build that into a Gatorade app. It tells them what kind of Gatorade they need to buy and how much of it they need to bring. So that's the point. And so they came by, kicked the tires, they liked what we were doing, and President of Gatorade is actually a Northwestern alum, lives around the corner from me in Evanston area. So it was a great relationship. We went off and they paid for us to do the tech development, develop the manufacturing. That's provided seed funding for us to launch this company. Again, very engineering product focused. And this was the first effort in that direction. And so they're very interested in quantitation. I was sort of surprised. They have Gatorade Sports Science Institute in Barrington. So they want to know exactly what is the accuracy and the precision of the measurement of sweat loss, sweat rate, and chloride by this colorimetric. So they wouldn't pay us until we proved, you know, it's scientifically accurate. And they have a whole stable of athletes that come through the Gatorade Sports Science Institute. And they have all kinds of conventional sort of lab-based approaches for determining sweat loss and chloride concentration. And this is, you know, it's human subject data, so some scatter here, but they're pretty happy with that. And the R squared is in the range of 0.9, 0.85, something like that. So it's pretty good. So scientifically validated. And then we went off and they gave the green light and we ended up making a product out of it. And one of the fun things about working with Gatorade is that an incredible stable of like celebrity athletes. And so this was the first commercial spot they put together on this, the Serena Williams wearing one of our devices there. If you like basketball, that's Paul George, that's Jason Tatum. Really nice there, drinking his Gatorade like he should. And then this is the best one, I am told anyway. I'm not a big soccer fan, but a lot of people are. This is Lionel Messi, right after but anyway, got your app, you take a picture, certain electrolyte level, so that's kind of cool. So they bundle this sweat patch with their bottle. They have these pods of different electrolyte levels. This tells you what type of pod to buy. Dump it into this bottle, backfill with water. You drink it up and you feel great and you perform better. That's the idea. So we've done about 3 million of these at this point. It's a reel-to-reel low-cost manufacturing approach, single use, and you can pick them up in packs. Each of these packs has 2 of these single-use microfluidic skin interfaced sweat monitoring devices. We focus on the cost structure around the device itself, and then we sell to Gatorade, and then they do the packaging, they handle the commercials and the promotion, the marketing, and the channel. And so I won't get into the details of what determines that number. We're not in control of that, but I think they set a pretty high price point because they want only serious athletes to be using this, but they also give them away at their camps and so on. And so I brought a couple of these with me. And so I'll give these away to the first two students who asked questions after my talk. So these are actually worth something. And so it's fun to play around with these. So be thinking of a question that you can ask and give them away to the first two. But I think the bigger business opportunity for Epicor is in worker safety. So think about like the industrial athlete, particularly oil and gas. These are pretty highly trained, sophisticated, skilled workers. They're operating in hot, humid environments for the most part. Dehydration can lead to workplace injuries and loss in productivity. And so as a safety tool, I guess, in that context, there's a lot of interest in monitoring sweat loss, electrolyte loss. In this particular case, a lot of times the devices are being used under PPE, so you don't have access, like optical access, take a picture. And so instead, Epicor guys have developed a little Bluetooth module that snaps on top of the microfluidic structure, and then it allows electronic readout and wireless Bluetooth transmission of the data. So first responders, oil and gas, manufacturing, mining, have a number of different customers in those spaces. This is the current customer list. Again, oil and gas, construction, manufacturing, transportation, logistics. United Airlines is pretty interesting. Anyway, they bought a bunch of devices. They're investors as well, and sports and research as well. So anyway, that's kind of what's going on there. There's the team. Again, I don't have any day-to-day with this, but it's really great collection of engineers focused on products and sales. Basically, again, it's not a VC-driven pitch deck exit strategy type of organization. It's just like trying to build stuff that's useful. The other thing, though, that I think would be great opportunity for them is thinking about medical. That's kind of what got us started. Let me give you one example of several that we're pursuing. One of the things you have to do is you have to correlate sweat to blood. Otherwise, nobody knows what to do with sweat because it's totally new. What do I do with a concentration of species in sweat? You need to know how that correlates to blood. In some cases, you get good correlation, in some cases not. And it really depends on a lot of the details. So you have to do the human subject studies to figure that out. So we are approached by nephrologists at Northwestern Memorial Hospital who are interested in chronic kidney disease. And for that disease state, what they do is they look at blood biomarkers, specifically serum creatinine and serum urea. And if the concentrations of those species are too high, then that's a good indication that that patient is suffering from kidney disease. But it requires a blood draw. So you have to go to the hospital, they draw the blood, they do so the whole idea would be to build a sweat-based microfluidic alternative to blood analysis that could be distributed for home testing. And so you need the chemistry for the colorimetrics. So we were able to develop that for both creatinine and urea. I won't get into details. You get a vibrant color change, again, over a physiologically relevant range of concentrations. And then you have to do the comparisons to blood. So this is ongoing, it's unpublished, but this is 12 kidney patients coming into the clinic for blood draw for a test of creatinine and urea in serum. And then while they're there, we collect some sweat. And then we do analysis of creatinine and urea in sweat. So that's what's being shown here, sweat concentration, blood concentration, creatinine, urea. And so you see pretty good correlation. There's an outlier here, got to understand that. But this looks to us to be very promising as an alternative to a blood test. So it's just kind of a representation of like where we're going, and where my own interest is more sort of in medicine rather than sports, but I think synergistic set of application opportunities. So for the last 5-10 minutes that I have, I'll talk about haptics, and which is a little bit more exploratory. I think it's interesting, and we're doing things to give you a sense of where we think the opportunities are. But before I do that, let me just show you how haptics comes into play. So for these devices, you're wearing them under PPE. You don't have visual access. In some cases, you don't even have wireless access because you're not carrying a phone around typically. And so there can be Bluetooth repeaters and sort of monitor things continuously. But what our customers wanted is some kind of alert that could make people aware of sweat loss that exceeds a certain threshold value. And so what was done here is they put a haptic motor in this device. This is just a little buzzer that goes off automatically because we have computational resources here. We can measure through the microfluidics how much sweat has been lost. We can compare that to a preset threshold value. When that amount of sweat exceeds that threshold, it just activates the buzzer. And so then the workers know, hey, I got to drink some liquids. I've lost a lot of sweat here. So that allows you to think about these skin interface devices beyond just a sensing capability to some kind of important, modest level of therapeutic function in that sense, in terms of awareness. And so that got us thinking again about haptics. I know there's some great work in haptics going on here, and it has a long history. So this is sort of the past. You have haptic interfaces in desktop, manipulators. Then you put haptics in handheld devices. A lot of work going on, haptic gloves and metaverse and this kind of thing. And maybe full body haptics going beyond the fingertips and the hands would be interesting. And maybe some of the epidermal electronics that we've been working on could be useful in that broader context. And so we begin to think about this and sort of dusted off some work that we did about a decade ago, initially thinking about electrotactile actuators to create a haptic sensation by electrically stimulating mechanoreceptors in the skin. And this is an example of sort of fingertip mounted haptic electrotactile actuators and little finger cuff. We had, more sort of epidermal electronics here on the forearm, is to creating a sort of a sensation of touch through pressure sensors in a robotic arm, and then that's activating haptic actuators here to allow you better control over the robotics. And the electrotactile was a natural thing to think about because it's electronic, so it fits very naturally into that overall engineering framework that I mentioned before. But the problem with electrotactile is there's a very narrow window between creating an onset of a sensation and feeling like you're getting shocked electrically. So it's not really the best way to do haptic. It's probably better to think about like mechanical actuators, and that's much harder. So there's a lot of activity in dielectric elastomers and piezoelectric actuators and soft pneumatics and different things like that. But for the most part, I think almost uniformly, the focus has been on the fingertips, which is great. But then we thought, well, maybe there's some opportunities to think about full body, like haptic actuators across your chest or on your legs or on your arms, things like that, maybe complement what's already being pursued by folks around the fingertips. And thinking about whether we could leverage all this, filamentary serpentine stuff for control electronics, wireless power delivery, and then tile up collections of haptic actuators that we could manipulate in a spatiotemporal sense, but in platforms that would be sufficiently sort of mechanically compliant to allow for a comfortable interface to the skin. So it's all the same type of games that I mentioned to you before. It's mechanics, it's materials, it's electrical circuit design, all kind of mushed together in some synergistic way. And I won't go through the details there. But one of the important aspects is not just the electronics and sort of the skin compatible mechanics, but what are you going to use as the actuators? And so our initial attempt in this area was not to develop a sophisticated actuator, but something simple enough, meaningful enough that we could create hundreds of them so we could begin to do system level tests and evaluations. A very simple Lorentz force actuator magnet, got a coil, got a little cantilevered structure here. We can adjust the geometry of that to set the resonance frequency. It turns out your mechanoreceptors have peak sensitivity around 200 hertz. And so we design it to resonate at about that frequency. It's kind of a buzzer, essentially. It's not the best, but something that we could go off and begin to build things with. And so you can make things that tile out in sort of different anatomical shapes. You can do large areas, different parts of the body. It could all be wirelessly powered and controlled. And then you'd ask the question, so and the tip of the finger, maybe you need millimeter separations. You have very high density of mechanoreceptors. What about the rest of the body? It turns out that the mechanoreceptors are very sparsely distributed across larger areas of the body. And if you can do a center-to-center spacing of haptic actuators in the realm of centimeter, half centimeter, you can do full body engagement. So you can really engage all of the mechanoreceptors across the body, except for the fingertips, the toes, and certain parts of the face, with really modest levels of integration and density. So these are 2-point discrimination thresholds, different parts of the body. You can see the calf, it's almost 4 centimeters in terms of that threshold condition. So you can do that, and then you can put these devices different parts of the skin. And the idea is you have like a touch panel that allows you to in real time control spatiotemporal levels of actuation, not only in terms of spatiotemporal sense, but also the amplitude of the actuation through pressure sensitive touch pads. So that's kind of the way it works. Here's an example of this being operated wirelessly through the internet in this case. So I have a postdoc in Evanston in my old labs in Urbana, And he's sort of in real time dragging his finger across this touch screen. And then that's replaying in real time a pattern of haptic actuation on this platform here on the outer forearm. And then he's drawing on the whiteboard what he's feeling, being represented here. So it's kind of the idea of how this whole thing works. And you could think about how you could maybe represent different modes of deformation of the skin. And here we have LEDs lighting up the actuators that are activated here, squeeze. And so it's kind of a little bit primitive, but you could begin to do this. And then you'd ask, well, can people really feel the difference between pinch and twist in that way? And so you can do psychometric surveys. And this is a truth table for that, different types of patterns, 6 patterns here. And it's pretty easy to tell the difference, multi-point stroking or twisting, different things like that. So as an information channel, there's maybe some opportunities using large area haptics. So what would be the applications? Maybe remote interactions beyond video and audio, social engagements, things like that. I think the sensation of touch is one of the most personal ways you can communicate with people, and maybe you could add that kind of touch, again, beyond the fingertips to the larger areas of the body. Entertainment, obviously, a lot of gaming applications, but we've been interested in medical, and so I'll just tell you what we're doing in medicine. Prosthetics control, I'll give you a specific example there. So here we have an amputee. This is an Iraq war veteran who lost his arm from about the elbow down. And so this is a robotic prosthetic arm controlled by EMG and has pressure sensors distributed in the fingers. Now, the question is, how do you transmit that pressure information to the individual in a form that allows him to act upon that? So you could grasp an object with sufficient force, but not too much force. So one of the challenges he had is he liked to hold his daughter, but didn't want to like crush her with his robotic hand. So being able to do that, it's possible by using a haptic array like this for sensory substitution. So in this case, we have haptic array wirelessly communicating with the robotic hand, transmitting information on the pressure distribution measured across the fingers into a corresponding pattern of actuation on the upper arm where he still has sensation. And so that turns out to work pretty well. It requires a little bit of training, as you might imagine. It's sort of not an immediately natural thing to think about, but this is an example of him going through training. So he's trying to identify the different patterns of force that are being transmitted to him as information through that haptic array on his upper arm. So you go through that, and then you say, well, what's a demonstration of this? So here's an example. He's blindfolded. He's trying to use his robotic hand, EMG control, to pick up an eggshell without cracking it. Now, if you can't see what's going on, you don't have any haptic feedback, it's basically impossible to do that because you always grip it too tightly, or you don't grip it enough. You can't pick it up. But then still blindfolded, now haptic actuation on, he can feel through the haptic actuator on his upper arm how tightly he's grasping the eggshell, and then use that to modulate the force that's being applied. Here's another example, similar type of thing, but this is for patients with diabetic neuropathy. This is unpublished, where it's sort of mounting pressure sensors in the base of the feet. These are patients who can't feel their feet, so they can't walk normally unless they're looking at their feet. And so the idea, again, sensory substitution, transmit high resolution pressure distributions measured at the soles of their feet to part of their body where they still have feeling and sensation, either lower back or upper legs is kind of what we're doing with that. And so this is some examples of patient studies at Shirley Ryan Ability Lab. Here they're trying to see how long they can balance without looking at their feet or holding on to this. And the haptics are on the outer arms there. So this is still ongoing, as you might imagine. It requires some amount of training, but these are sort of the levels of improvement. Not everybody got better, as you might imagine. There's some variability, but without feedback, with feedback, how long they can balance. And so most subjects have improved. Anyway, sort of unpublished work at this point. So I think I'll wrap up 2 more slides. So if you think about the skin, there's a tremendous level of sophistication in the engineering design. So you can feel not just buzzing, but normal force, shear force, torsional force, different frequencies of force. You can feel heat patterns of heat as well. And so it creates all kinds of different opportunities to build small scale actuators that allow you to control the kinds of forces that are delivered to the surface of the skin. And this is one example where we have a bistable magnetic actuator, we can push on the skin with a fixed force, or we can vibrate, or we can add a origami structure to allow us to twist the surface of the skin. And so that's an example of what we've done. And here we're using the LiDAR function in the phone to provide visual, sort of non-visual capability to navigate an environment that's visually impaired. So the phone is scanning the environment, it's transmitting information on where objects are located to the haptic array, which is mounted on the back of the neck here as an example. And then this is probably our most sophisticated actuator at this point. So it includes a tri-coil nested assembly that allows us to deliver magnetic fields of various orientations to a magnet that's in contact with the skin. So we can vibrate it laterally, vertically, we can rotate it, we can control the frequency, we can create static force as well. And so there are a lot of things you could do. And then in this case, we have an accelerometer on the back side, so we can sort of do closed loop control as well. So I'll just conclude. I mean, I think this is supposed to be kind of an interdisciplinary group here. And I would just highlight there's just tremendous opportunities in these kinds of areas for everyone to participate. So, it's materials, it's mechanics, it's sensors, it's power electronics, it's wireless, it's circuit design, it's software, it's firmware, it's machine learning, and it's all, I think, in the context of efforts that, if successful, could have some broad societal benefits associated with them. So this is kind of why we are excited about this broader area. But with that, I'll just conclude. I think I went a little bit too long. I apologize for that. But these are the senior collaborators. We're a very collaborative group. So engineering science, mentioned some of those folks, with clinical science, sports medicine, probably the most important collaborations. We have large group, great students, really hardworking, great creative people. Baoxing is a great example of the kinds of students I've been blessed with, postdocs over the years. And so I always like to conclude by thanking them for their attention, and also thanking the foundation for making this lecture possible, and just thinking about Jefferson again. So thanks very much for your attention. Don't forget sweat patches.
Thank you, Dr. Rogers, for the excellent talk. I just had one quick question regarding the epidermal electronics. So you said that they were wireless and they had a data acquisition unit as well as a power supply. And so I was wondering if you could give an idea as to the auxiliary electronics required to operate it. Like, is it a large device? Does it require a lot of power to supply the actual electronic, et cetera?
Yeah, great question. So we use a transmission system that's borrowed from the RFID industry. So it's 13.56 megahertz. It's pretty conventional power electronics. It's not a lot of power. It's a few watts, 13.56 megahertz. The antenna is typically mounted in the base of the isolate underneath the bed. And so it really kind of covers the isolate in terms of area and volume. We've got 30 to 50 centimeters coverage in Z. And pretty much the entire, bed is covered also. So it's great for that particular application. You kind of know where the baby is. It's not, fully ambulatory compatible. You kind of have to assume you know where they are and you position the antenna appropriately. So that's one piece. The other piece is the receiver unit. And so you can configure like a tablet or even a phone to allow for, near field communication readout. I mean, it's the same NFC that's used for wireless payments. So, and that was done explicitly because if you think about cost, you think about Africa, you don't want to have to pay for a separate monitor. And if you can use the phone, everybody has a phone. So we kind of leverage that. Now that's what we're doing for the battery-free devices. For the battery-based devices, they need to be constructed a little bit more robustly to allow for many hundreds of cycles of use, as I mentioned, from an economic standpoint. So they actually have a small rechargeable lithium polymer battery built into them. And we have wireless recharge capability because the devices have to be totally sealed because there's biofluids, all kinds of things. You can't have, a charge port or something like that. So we do that, and in that case, it's just a straight Bluetooth link to the phone or the tablet. So that's kind of how we've engineered things. So yeah.
Thanks
So
so
if
much.
you want a sweat patch, you get one. You look kind of athletic, so very good. Yeah.
Hey, Dr. Rogers, thanks for the talk again. I had a question about the sweat patch technology. So, you mentioned that you know when you were testing it, you had almost like you were able to get the whole thing full essentially. So my thought there is that you know everyone sweats at different levels. So
Yeah,
how is the like I guess the patch scaled for like different people? And
yeah.
also the follow-up is can you like empty it or like is it one-time use kind of thing? So
Yeah, great question. So I actually have in my bag the original sweat patch that we launched with Gatorade turned out to be pretty hard for most people to fill. So it was really built around kind of elite athletes that were coming to the Gatorade Sports Science Institute. So for me, it's impossible. I could not fill one of those. I mean, this is a little bit different. You know, I could exercise, and I sweat a lot, actually. I'm a heavy sweater in terms of the spectrum. But you know, I could sweat, you know, 1.5 liters. That's about an hour and a half intense workout for me, and I would only have half the sweat patch filled up. And then if that same device were used on, I don't want to make generalizations here, but our experience is that Asian women almost don't sweat at all. Then it's not useful at all for them. So you have to kind of find a sweet spot. The latest devices attempt to do that, to kind of one size fits all, but it's not perfect. So what we've done, like really simple idea, is you can continuously grade the dimensions of the channel. So you have very narrow cross-sectional dimension right near the inlet, and then it can splay out both in width and in height. And so that provides a wider dynamic range, I guess, is one way to do it. The other way to do it is you just have multiple inlets. So some of the inlets have a very small opening. You're only capturing a small number of sweat glands, others a little bit larger. And then you have different channels for low sweat, medium, and you know, significant amount of sweat. So those are the approaches that we've used. It's just kind of a balance. The other question was around reusability. These are not reusable because the dye that's located in the inlet port gets consumed. Actually, if you look at this, there's kind of a gradation in dye concentration. So you get this really bright orange color at the fill front. And then by the time, you know, a substantial amount of sweat has flowed past that inlet, you end up with a much lighter color here. So if you were to try to use it again, most of the dye is already passed out. And then the colorimetric assay for chloride is just a single use. So multi-use, I think, is interesting. We were able to drive the cost structure of these devices down to a low enough level that it's compatible with single use. You have to worry about recycling and waste and things like that. So we did publish a paper. We built these kinds of devices out of compostable polymers that sort of degrade in the soil. So you can kind of deal with things in that way. And then it's such a practical aspect of like cleaning the sweat out. It gets a little, you know, messy. You know, think about contamination and things like that. But those are the considerations. There are also ways to build devices that we're working on now that don't rely so much on, you know, an extended microfluidic channel. It's a little easier to clean. And then if you're doing electronic readout, you know, you don't have to worry about consumption of the dye or the colorimetric reagent. So I think multiple use devices, that's an area of opportunity for, you know, new ideas in engineering. So great question.
Thank
You
you.
get one of these if you want.
Thank you. My question is regarding more of, you talk a lot about haptic actuators at the end, but I'm more thinking about haptic sensors, very thin film sensors for haptic interactions. This is where I'm a PhD student, this is where my research is. I'm wondering about if you were trying to measure some sort of haptic interaction with a thin film sensor, such as one of the pressure sensors, have you been able to quantify or psychophysically measure the impact that these sensors have on the tactile acuity, touch interactions?
Yeah, that's a great question. Again, we've stayed away from the fingertips just because it's a really crowded space. I didn't see a great way to contribute beyond what, you know, groups like yours and others have done in that area. So we haven't had to worry about that so much. I know there's some papers from Takao Sunia's group, University of Tokyo, where he's shown, you know, pressure sensors that can be placed on the fingertip, but they're so thin and soft, almost kind of the epidermal story again, that it really doesn't change the tactile acuity, I guess, in terms of your sensation. So there's been some great work in that area, but it hasn't come from our group. You know, I think it's super interesting, but I could only kind of refer you to other publications. I think it's a great topic to work on, though, for sure. Yeah,
Thank you.
yeah.
Yeah, maybe give a time being, maybe just one last question, and then
Yeah.
after that, John will still be here, so you can have a chat with him right here.
Yeah, thank you. So I'm a physical and materials chemist, and so I'm thinking about atomic level interactions and the structure and things like that when I'm looking at your talk. And it's very interesting to see all of these multi-level materials chemistry going on here. So thinking more about this stability, reusability from a stability point of view, I guess I'm wondering, are there any kind of parallels to be drawn from the vast literature in the recent years in in photovoltaics in particular, for example, and thinking about tailoring surface structure of these, silicons, and, many other species. And I saw at some point that silicon ribbons came into picture. Do you kind of see a way forward in being able to potentially design and better understand, surface interaction, especially now when that is in contact with, biochemical, materials and in the body, tissues and whatnot?
Yeah.
Yeah,
Yeah.
I guess, yeah. Is there a way to kind of understand what's going on there and accordingly rationally design?
Yeah, I think it's a great area of opportunity. It's funny because you put your finger on, I think it's probably the critical material at this point in these devices is the material that contacts the skin. It's the adhesive. It seems like it's maybe not the kind of sexiest thing to study compared to the electronics and the sensors, all these different things. But from a cost standpoint, the adhesive is just single use because once you peel it off, it's totally contaminated with all kinds of dead cells and residual sweat and all kinds of stuff. So it totally loses its adhesive capability, and also you have to worry about contamination, infection risk, and all this kind of stuff. So the adhesive is just single use. But if you look at the cost structure, especially for LMICs, it's the cost of the adhesive that dominates the cost of patient monitoring. So any kind of low cost adhesive, skin compatible, needs to avoid irritation, all kinds of requirements. So maybe surface texturing would become important in that case, or if there was some way to refresh the surface or some kind of chemistry that would degrade the dead cells and sort of autonomously kind of refresh itself somehow, that would be super valuable, I would say. I don't know exactly how to do that. The other aspect, though, is in terms of how long you can keep these devices on the skin in the first place. So the skin itself is time dynamic. So it's a cellular escalator where cells are differentiating from the base layers of the skin, emerging to the stratum corneum where they die to form a biofluid barrier. But if there's a device sitting on top, over the course of days, the thickness of that dead cell layer is increasing. And so you end up with a less and less mechanically stable interface because those dead cells are not adhered to one another very well. So it goes beyond just the material. You have to think about what's going on with the biology and try to figure out an adaptive material somehow that can change in properties in a way that can accommodate that cellular sort of dynamic set of processes. So great question. I mean, I don't know. It's a space where sort of some good ideas could really move the needle, on the technology. So I'd encourage you to think more about that. Maybe you can come up with some.
Thank you.
Yeah.
Thank you so much again. Since Professor John Rogers will still be here, so if you have a time during the lunch, you can talk with him for questions. And then before that, I think that we have some guests to you. It's very unique, the Jefferson Cup and designed by Tom Jefferson. So
Wow. Okay. Thank you very much.
Thank you so much.
Yeah, appreciate that. Thank you. Yeah.
Go right through this board and just do a big circle around the table. Please enjoy the food. John will be here for a few more minutes to answer any questions. And thank you again so much for coming.
Shopping, so I'm just pick me up.
Okay.
Later on. Yeah, but I'm gonna see if I can also.
Yeah,
Go back to the department. Yeah.
I know, I know, like, yeah, you just throw these things on the city. Isn't it just stuff? If I was there, I guess help. That's.
She's taking it.